Beneath the vast celestial expanse, a huge scarlet star sits in the middle of the most visible and simple-to-identify stellar bodies, asserting its power. Far beyond the horizon, along the outer edges of our full understanding, this immense cosmic entity possesses the capability of releasing a magnitude of energy that could rival an individual's combined radiance. This galaxy's infinite array of stars includes astronomical giants, one of which may be about to undergo a catastrophe of unimaginable scale, a burst so massive that it could surpass 1 billion suns in real energy output. The question is, are we ready? The aftermath of such an event might result in devastation. This colossal red star, often referred to as Goliath, is in close proximity to Earth and has emerged as the focus of significant debate and fascination within both the scientific community and the general public. In recent times, this star underwent significant transformations, raising more and more concerns among researchers and fueling intense discussions about its future trajectory. The most alarming possibility is that this change may indicate the explosive early stages of a supernova, a dazzling event that marks the final phase in a star's life cycle. This star, known scientifically as Alpha Orionis, would, if it exhausts its nuclear fuel, collapse under the force of its own gravity, resulting in a catastrophic explosion. Just the idea of this event not only causes anxiety among scientists, but also among those of us inhabiting Earth, given the potential repercussions. Alpha Orionis, easily recognized by its deep crimson hue, is considered the largest and most radiant star in the Orion constellation. With the help of cutting-edge instruments like NASA's Hubble Space Telescope, astronomers have closely observed its behavior, especially in 2019, when it suffered a significant loss of brightness. This phenomenon, rare among stars of this type, raised alarms among scientists all over the world. Whereas our Sun frequently undergoes coronal mass ejections, the unusual event witnessed in Alpha Orionis has sparked a re-evaluation of what occurs during the last few years of a huge star's life. Scientists are currently divided over the exact distance of Alpha Orionis from Earth. Estimates vary, with some placing it as far as 1,200 light-years away, while others suggest it could be as close as 724 light-years. The difficulty in accurately determining its position lies in the vast distances involved and the peculiar nature of red giants. Despite concerns regarding the star's activity, Alpha Orionis continues to be one of the most awe-inspiring objects in the night sky, shining multiple times more brightly than our Sun. But this luminous glow comes at a significant cost. It is consuming its nuclear fuel at a rapid pace, speeding up its journey toward the inevitable end of its life cycle. Once it runs out of fuel, the star will likely collapse, possibly forming either a neutron star or, in a more catastrophic scenario, a black hole. As the explosion progresses, a pressing question arises. Could Alpha Orionis pose a threat to Earth? If a supernova were to occur within just a few light-years of our planet, the consequences would be devastating. A supernova can release an unimaginable amount of energy, possibly surpassing that of entire galaxies, with far-reaching consequences. Even if Alpha Orionis lies at a significant distance from Earth, history reminds us of the potential danger. The last supernova event recorded within our galaxy took place in the year 1604, and since then, humanity has not witnessed a similar occurrence on a local scale. However, in 1987, a supernova exploded in the Large Magellanic Cloud, located 169,000 light-years away. Despite the distance, the explosion had significant effects, although it posed no direct threat to Earth. Nonetheless, these rare events serve as potent reminders of the immense scale of supernova explosions and their potential dangers. A supernova occurring close to Earth could create what has been termed a danger zone. The dangers to life on Earth, however, must be viewed within the larger cosmic context. While supernovae are infrequent occurrences, gamma-ray bursts, GRBs, represent an even more potent threat. These bursts are capable of destroying entire biospheres by flooding planets with deadly radiation. For instance, GRBs could destroy a planet's ozone layer, leaving it exposed to harmful ultraviolet radiation from its sun, effects that could persist long after the burst has subsided. This looming threat has become a focus of recent research, shedding light on the hazards associated with stellar explosions. When enormous stars explode as supernovae, their brightness can surpass that of entire galaxies. This intensity raises an important question. What would happen if a similar change occurred in Alpha Orionis? Should it explode, it could become the second brightest object in the sky, even visible during daylight hours. The energy released could be so intense that it casts shadows at noon, offering a striking yet unnerving experience. While the visible light from a supernova would certainly be awe-inspiring, the real threat lies in the high-energy radiation, gamma and X-rays, that would accompany such an explosion. This radiation could deplete Earth's protective ozone layer, leaving it exposed to dangerous levels of ultraviolet light and leading to mass extinction events. The dangers posed by a supernova don't cease with the explosion. Its remnants, shock waves traveling at nearly the speed of light, could continue to spread destruction throughout the solar system, further harming the ozone layer and increasing Earth's exposure to radiation. In addition, the long-term effects of a supernova's energy release could linger for centuries. Studies indicate that Earth may have already been affected by such events in the past. Elevated levels of iron-60, a radioactive isotope created in supernova explosions, have been found in lunar soil and deep-sea sediments, suggesting Earth has encountered the aftereffects of such occurrences, possibly in the last few 100,000 years. Currently, there are no known supernova candidates near Earth that pose an immediate threat. However, ongoing research continues to uncover new potential risks, particularly from long-range, radiation-emitting supernovae. These lethal explosions occur when a dying star is enclosed by a vast disk of material, and the waves from the explosion interact with this material to produce powerful X-ray radiation capable of traveling vast distances through space. The effects of this radiation could impact planets within a 150 light-year radius. Thankfully, no such candidates have been found in our neighborhood. Nevertheless, the study of these events has provided new perspectives on the concept of habitable zones, the regions of space where life-supporting conditions may exist. It appears that these zones might be more restricted than initially believed. The outer regions of galaxies often lack sufficient star formation activity to encourage the creation of rocky planets. Conversely, the inner regions, where stars are born and die more rapidly, may pose risks due to regularly occurring supernovae. As researchers continue to investigate the remnants of supernovae, they're discovering that these cosmic remains can give rise to new stars. The expelled material from the explosion creates stellar nurseries, emphasizing the interconnected nature of the universe, where the death of one star often leads to the birth of another. These elements, forged in the heart of dying stars and scattered across galaxies by supernova explosions, eventually become part of planets, moons, and even living organisms. In fact, much of the iron in our blood and the calcium in our bones originated from the remnants of ancient stellar deaths, highlighting the deeply interconnected relationship between cosmic events and life on Earth. This concept, that we are literally made of star stuff, was popularized by astronomer Carl Sagan and is now supported by a growing body of scientific evidence. It underscores a profound truth: the life cycle of stars is not just an astronomical process, but a foundational element of biology and chemistry as we know them. As supernova research advances, it is opening new windows into the early universe. Observing distant supernovae allows astronomers to peer back in time, to an era when galaxies were young and star formation was rampant. These studies not only shed light on the origin and evolution of galaxies, but also help refine our models of how the universe itself formed and expanded. One major area of focus is the mysterious force known as dark energy, the phenomenon believed to be driving the accelerated expansion of the universe. By measuring the light from Type Ia supernovae in distant galaxies, scientists can map the rate of expansion over billions of years, bringing us closer to understanding the true nature of dark energy. Meanwhile, in our own galactic neighborhood, monitoring potentially volatile stars like Alpha Orionis remains a top priority. Space-based observatories, such as NASA's Hubble and James Webb telescopes, along with ground-based arrays, are constantly collecting data on light emissions, temperature fluctuations, and atmospheric composition. The hope is to detect early warning signs of an impending supernova, giving scientists, and possibly even civilians, the chance to prepare for potential effects. While it's unlikely that any such explosion would cause mass extinction unless extremely close, the electromagnetic pulse and cosmic radiation could interfere with satellites, GPS systems, communication infrastructure, and even power grids. In a worst-case scenario, a nearby supernova could strip away parts of Earth's atmosphere or induce a surge in solar activity. However, much of this remains theoretical, as the rarity of nearby supernovae means we have little direct data on their local impacts. Still, the possibility is enough to drive international collaborations focused on space weather preparedness. Agencies like NASA, ESA, and others are investing in early detection systems, atmospheric shielding technologies, and robust global monitoring networks to safeguard against cosmic threats. In parallel, public engagement with these phenomena is growing. Planetariums, documentaries, and science museums are increasingly weaving the awe and danger of supernovae into their narratives, fostering a deeper appreciation of the universe's power and our place within it. Ultimately, the story of supernovae is a story of transformation. From destruction comes creation. From cosmic chaos arises structure. And from the death of ancient suns comes the raw material for new worlds, and perhaps, new life. As we look to the sky and wonder about the fate of Alpha Orionis and stars like it, we are reminded that the universe is not static. It is alive, dynamic, and forever evolving. Our task is to continue observing, learning, and preparing, for in the heart of a dying star lies the seed of cosmic rebirth. Mediums enrich the subject matter that eventually forms new stars, planets, and, without these heavy elements, life itself. Components of the solar system, and even our own existence, would be impossible without them. Therefore, supernovae are not just destructive events, they also play a vital role in the creation of the very elements that compose the planets and stars we observe today. Supernova research is also being studied now and has improved our comprehension of the universe's expansion by observing the brightness of supernovae of type Ia, caused by the explosion of a white dwarf. Astronomers have the ability to measure cosmic distances with remarkable precision. These standard candles have changed the way we map the universe by supplying essential information about dark energy. Despite the rapid expansion of space and substantial advancements in our ability to determine cosmic distances, the dangers that a supernova could pose cannot be ignored. Despite the minimal likelihood of a nearby supernova impacting Earth, the long-term consequences of such an explosion may be significant. As mentioned earlier, supernovae emit intense radiation that could affect the solar system's environment. This radiation could interact with the Earth's atmosphere, depleting the ozone layer and exposing life to harmful UV radiation from the sun. Without the ozone layer, Earth's survival could become increasingly difficult, if not impossible. Additionally, the shock waves from a nearby supernova could interfere with the structure of the solar system. These waves could compress interstellar space, potentially triggering the formation of new stars or altering the orbits of objects within the solar system. In the worst-case scenario, a nearby supernova could disturb the delicate equilibrium of the solar system, resulting in catastrophic shifts in planetary orbits and possibly even posing a threat to Earth's existence. The study of supernovae and their remnants also raises fascinating questions about the universe's future. As stars die and supernovae occur, their remnants can eventually form black holes or neutron stars, some of the most mysterious and extreme objects in the cosmos. Black holes, in particular, are areas of space where the force of gravity is so great that not even light can escape. These objects are thought to be the final stage for the most massive stars, and their formation is one of the most fascinating phenomena in modern astrophysics. Despite their destructive nature, supernovae are crucial to the ongoing development of the universe. The materials they release into space serve as the foundation for the development of new stars and planetary systems. As new stars are created, the stellar cycle of life and death continues to drive the development of galaxies, contributing to the ever-expanding nature of the universe. In the midst of the potential threat that a supernova explosion poses, however distant, it remains essential to study these events to advance our understanding of the universe. Supernovae not only provide valuable insights into the life cycles of stars, but also offer important information about the chemical composition of the cosmos and how galaxies evolve over time. As we continue to explore the vast reaches of space, our understanding of these extraordinary cosmic events will deepen, offering a clearer and more encompassing perspective on the universe's past, present, and future. It is evident that studying enormous cosmic events like supernovae will continue to reveal new layers of understanding about the universe and its intricate mechanisms. Each step forward in this understanding is made easier by research into the true nature of stars' lives and deaths. Their consequences, like neutron stars and black holes, represent some of the most intriguing and enigmatic aspects of astrophysics. These phenomena raise profound questions regarding the ultimate fate of stars and their role in broader cosmic processes. The explosion of a supernova involves extremely intricate nuclear physics. Despite the vast distances across which their effects are felt, they influence the entire process of galactic evolution by sparking the birth of new stars and enriching the cosmos with essential elements. Understanding how these events occur and the circumstances that lead to them helps scientists piece together the puzzle of stellar evolution. In addition to their role in star formation and element creation, supernovae serve as crucial tools for measuring cosmic distances. By studying the light from these dramatic explosions, astronomers can create more accurate maps of our universe, track space's growth, and study the distribution of galaxies. These measurements, which cover extensive distances, are essential in determining the age, scale, and structure of the universe. They have also led to revolutionary discoveries regarding the mysterious force known as dark energy, which appears to be accelerating the expansion of the cosmos. This ability to measure distances using supernovae has had ripple effects across astrophysics by providing more detailed and reliable methods for gauging distances throughout the universe. We've gained a better understanding of how quickly the universe is growing and how galaxies are evolving. Evidence of dark energy's existence was first inferred through observations of distant supernovae, suggesting that the cosmos is not only expanding but doing so at an accelerating rate. Despite the incredible knowledge gained from these supernova studies, the potential risks from a nearby explosion remain a fundamental concern. Even though such an event is unlikely in the immediate future, the possibility, however remote, deserves our attention. The destructive effects of supernovae, particularly the radiation and shock waves they generate, can have significant impacts on nearby planets. If Earth were to fall within range of such an event, the consequences could be catastrophic, from the destruction of the ozone layer to disruption of the solar system's careful balance. Recognizing these risks forces scientists to think deeply about the possibilities for life on Earth. If the ozone layer were compromised by cosmic radiation following a supernova, Earth would no longer be protected from harmful ultraviolet rays, potentially resulting in widespread environmental and biological damage. This presents a serious threat to life as we know it today, making it necessary for scientists to continue researching supernova hazards and other cosmic dangers. Some scientists even propose that early Earth may have suffered from similar devastating events in the past. Isotopic evidence found in ancient geological layers suggests our planet has encountered the remnants of past supernovae. This means that supernova explosions are not just theoretical risks, they may have already impacted Earth's history. Whether past supernovae contributed to the development of life on Earth or caused mass extinctions remains a topic of debate. However, the possibility that these cosmic explosions have influenced our planet's history adds another layer of intrigue to the study of supernovae. As research into supernovae and their aftermath continues to evolve, astronomers are also studying the effects of gamma-ray bursts, which are even more powerful and destructive than supernovae. Gamma-ray bursts can release immense amounts of energy in just a few seconds, significantly more than a typical supernova. They possess the potential to sterilize entire planets by eradicating their atmospheres, including the ozone layer.